Yeah, thank you so much. My name is Tarek Mehrez, and with my colleague Carsten Hansen, we're both machine learning engineers. We work at Textkernel, and we encountered this problem as a machine learning team on how to train the machine learning jobs, how to scale this, how to manage these jobs, how to make things as smooth as possible for a machine learning team. So we had the right hardware, and we had the people who are doing the modeling, but we couldn't really figure out how to do the organization in a proper way. And that's where Kubernetes came in as a good tool to manage these kind of jobs. So the aim of this talk is not to introduce Kubernetes. So I'll be touching upon some of the interesting features, like the scheduler, and that's the main feature that we'll be focusing on from Kubernetes. And we won't be really covering the internals of TensorFlow, so we'd like to be as framework agnostic as possible. So these concepts should apply to any of the other frameworks that people use, whether deep learning frameworks or other machine learning tools. So the whole idea is how to manage and scale these jobs. So basically how to automate the pipeline to fire these jobs, start them somewhere, and make the training process as smooth as possible. But before we start, I'd like to take a step backward and start by what Textkernel is actually doing. So as some of you know, Textkernel is doing solutions in the HR domain. So we're parsing CVs, we're parsing vacancies, and we're matching both together. So the whole idea is based on sequence labeling problems. And as you see here, we have a PDF, a typical CV, and I'd like to have this nice data structure that contains your information that people use afterwards as recruiters in search engines and so on. So we have a lot of machine learning jobs based on TensorFlow. And we have this new wave of deep learning models based on BiLSTMs. And these are basically TensorFlow implementation. And we support a lot of languages, like 18 languages, I think, or even more. And we have a core machine learning team of 13 engineers doing these training jobs regularly. And each language is not actually one model, it's a stack of models. So we have, I don't know, I think 6 models per language. So as you might have guessed, we have hundreds of TensorFlow jobs to train. And let's start by defining what is a real-world machine learning system. So this is something that we also encountered, that we kind of simplify what data scientists are doing. So we have this nice machine learning block where we do the actual modeling. But in fact, we also have a lot of other things to care about, like the data verification, like the resource management, process management, and so on. And I kind of want to differentiate between, let's say, the left part where you do the preparation, the part in the middle where you do the training, and then on the right where you do the serving. And I think yesterday there was a talk about how to monitor these models in production, but that's not really the focus of this talk. We're kind of focusing now on the resource management, like the hardware management and process management. So how to do this during the training part, during the training phase. So as a machine learning engineer or as a data scientist, I don't want to really babysit my jobs. I want someone to take care of this for me. And this is where, again, Kubernetes come in. So what is it all about? We want to have separation of concerns. So machine learning modeling should be different than machine learning operations. I mean, people can do both. People can know how to do both. But ideally, the data scientist shouldn't really worry about what's happening under the hood. So as a data scientist, if I have a TensorFlow graph and I have a config file in my hand, I would like to send this to some black box that would run my compute-intensive training job in a convenient manner. And that's the whole point. So as easy as possible, which means with the least possible steps, but also as fast as possible. So how can I utilize my hardware? How can I make use of the hardware we have as a team? Nope, you want to take a picture? So the whole talk is, what do we need to have in this black box? What do we care about? So first fact, more CPUs for us, for the TensorFlow graphs that we've been using, meant faster epochs. So doubling the CPUs almost got us half the time per epoch. And that's why we wanted to scale outside of your laptop. We want to go to some other scalable hardware. One other fact is the hardware is there, as we mentioned, but the question will be, how do you organize this usage between data scientists and the hardware and the machines? So this is how we want to sketch out the talk. We have how we did it before Kubernetes, and what kind of headaches did we encounter. And then we're going to define what Kubernetes is. Again, not as an entire framework, but rather what we're interested in. And then we go a bit into the details of how to manage these jobs, how to scale these jobs, and so on. So let's start by before Kubernetes, what actually happened, what was the case beforehand. So I'd like to formulate this problem as the typical machine hunt, as we call it. So we have this cluster of virtual machines that we own as a team. And then we have this data scientist, who we'd call Luigi in this case. I think he's not here today. But So Luigi wants to train his machine learning model, right? And he wants to find a machine where he can train this model. The question will be which one. We have different specs per machine. Some machines have more cores, some machines have, I don't know, typical general purpose machines and so on. So the question is, how do we check which machine to run on? That's one question. And the other question is it actually free or is it being utilized? And if it's free, then I can start my job. So I will start with the first one, but it's actually busy. So this is the manual steps that we've been going through beforehand. And then we check some other machines, and they're still busy until I find one which is free. And then I go in there and schedule my job. So in this case, if you have another data scientist who wants to use also these machines, this cluster, in this case, it's not possible because all of them are busy. So Alicia will have to wait in this case. She's also not here. So that's, as you might have guessed, we are in desperate need of a proper scheduler. So that's the whole point. So that's one step. The next step is, OK, we found a machine. We want to start things now. We want to start the new job. What are the steps so that Luigi can start his nice job on this machine? So, OK, the typical steps that Luigi would SSH, create the conda environment, pull some code, pull the data, start the job. These are usually, beforehand, they were basically manual steps. So that wasn't really scalable in that case, because for one person, that's fine. But if you have an entire team that would like to do this in an automated manner, that wasn't really possible. So yeah, a lot of steps. So where the problem is, what is actually the problem in this case? So we have a lot of data scientists. We have a big machine learning team that we want to enable in order to train these models in a smooth way. And the machine specs are not always standardized, as I mentioned. So some of them have, I don't know, 40 cores. Others have 8 cores and so on. And I would like to utilize these machines. And data scientists don't always train single model at a time. So I'm not sure who's training what. And are we training a lot of models, no models, one model? So these kind of questions, I don't want to worry about this. I want to automate this process. So more data scientists, more models, scheduling is hard. That's the main problem that we have. So the reality is, again, we have a lot of data scientists, a lot of machines with different specs, and we need an intermediate layer to choose the right machine, but also prepare the environment, start, monitor the jobs, and babysit these jobs in the sense of, if one of these jobs failed, how can I restart this automatically without worrying about where can I do this and how can I do that? And this is where Kubernetes came in. So Kubernetes was a nice tool that we were actually using for other purposes, like server microservices, running CI, CD jobs, and so on. And we thought it's a perfect, that's a perfect use case for it, actually. So what is Kubernetes? Yeah, this actually brings us to an interesting question. Who knows what Kubernetes is? Cool. Who trained models on Kubernetes before? OK, like 4. So for those of you who know what Kubernetes is, I'll just be focusing, as I mentioned, on a scheduler. And of course, we have this mainstream definition that it's a container orchestration framework, of course. But what does that actually mean? So let's imagine that we have a cluster, right? You have some nodes, and these nodes have Kubernetes installed on. So it's a framework that manages these nodes, this cluster. The idea is that I can actually give labels to these machines. So I can say, label node number 1 of type machine learning, which means that node number 1 can hold machine learning workloads. So why is this useful? Because then I can make the scheduler know which machines to use according to the workloads I'm getting. So if I know that that's a CI/CD job, it doesn't really have a priority, so run it in a low priority machine. Or that's a microservice and it requires some sort of specs, then I know where to run this, because then I can tell the scheduler what kind of machine to run on. And this doesn't have to be the case. So if you didn't tell the scheduler what to do, in the sense of labeling these machines, it will still figure out which nodes to rank and accordingly schedule the containers. So you have jobs as containers, and in this case, these jobs are our TensorFlow containers. So they contain the TensorFlow graph with the environment, with the conda environment, installed dependencies, and everything there. It's basically ready to start. So it's ready to be run on Kubernetes. And then we have a scheduler in between that would choose among these machines, which one do I want to use in order to run one of these containers? So the question here is, what is the scheduling criteria? What do I need to worry about? So one thing, which nodes has machine learning labeled? So as I mentioned, we label these machines according to the specs, and then I ask, OK, which of them has the label machine learning that I can use to schedule this job? That's one thing. The other thing is, again, out of these ML nodes, which of these are being utilized? So remember Luigi, when he was trying to find a machine, the whole point was which of these machines is actually empty right now. And I'll go a bit into the details further on why we need these machines to be empty, because a very basic question might be, why not just schedule 2 jobs on the same machine? And the answer is because we configured TensorFlow to utilize all of the CPUs on the same machine. So if you give it 40 cores, TensorFlow would just take the whole machine, like the entire 40 cores, to train the jobs. And that's why we didn't want 2 jobs to be on the same machine to compete for resources. And then schedule, basically, the next container on the next free machine learning node. If I found none, I would basically queue these. And the scheduler is also doing the queuing for us. So we don't have to worry about when to schedule these if they're being queued. So it periodically asks the machines if they're free, and accordingly it will do the scheduling. Okay. So one other way to view Kubernetes is it's basically an abstraction layer between your hardware and whatever you want to run. So as I mentioned, we ran Jenkins executors, we ran Dask workers, we ran microservices or TensorFlow jobs. So Kubernetes doesn't really care what is it running in most cases. So it only ran containers, right? So it doesn't really care what's inside these containers. And that's the good thing about it, that you can have multiple workloads of different types running on the same machine, cluster, not machine. Assuming, of course, that we did the kind of scheduling constraints that we viewed here. So that's why we needed these constraints, to make sure that these workloads can peacefully run together in the same cluster. So that was one thing on how to define like what kind of features are we interested in from Kubernetes itself. And then the next question will be, how did we manage these jobs? How did we overcome the problems, the manual steps that we've been through before? So in order to do this, we need 2 things. One of them is the Docker file, which is basically the definition of the container. And the other thing is the Kubernetes config, which is basically a deployment file that we use in order to tell Kubernetes what to do in this case. So what should be the scheduling constraints, what should be the scheduling features that we're interested in to run this job. So let's start with the Docker file. It's actually pretty basic. So you have the repo, which you basically pull. Actually, I can go to the bash script right away. And in this case, you clone the TensorFlow graph alongside the config file that you have. You install the dependencies, and then you basically start the tuning. Now, the main question would be, why did I do the cloning on runtime instead of build time? And the answer is, well, it doesn't really matter, because if we have 3 days of training, if I spent 1 minute pulling and running the dependencies, it won't really make a huge difference. That's one thing. And the other thing is, I didn't want to build a new Docker image every time I have a change in my TensorFlow graph. So in this case, I can only have 1 Docker image for all types of TensorFlow graphs that I'm training. So the next thing is the Kubernetes config. So first thing is we will pull the image. So I now push this image as RNN training. I gave it some version. And the next thing will be how to run this container, how to run it in Kubernetes, right? So I pull the container. So in the definition, I tell Kubernetes which container to run. That's one thing. The next thing is the affinities. Remember the 2 constraints that we mentioned, that no pods, no 2 containers can co-occur within the same machine. And we're interested in the machine of type machine learning. So scheduler only can run 1 training job on 1 node at a time. So in this case, I said, OK, I'm interested in all jobs of type RNN training, which is basically the type of the container I'm running. And then here I said pod anti-affinity, which basically means don't run, so that's a negation, basically. So don't run these jobs together on the same host. Because again, I configured TensorFlow to consume all CPUs. So I don't want them to co-occur and compete for resources. So that's one thing. Another thing is, please run on machine type machine learning. So basically, these are the constraints, or these are the features I'm interested in order to run this container, this job on Kubernetes. Of course, I stripped away a lot of details, but this doesn't really matter for this talk. I think it's outside of the context. But we're only interested, again, in these 2 constraints. So what's actually happening there? So we have now the Docker file. We have the Kubernetes deployment. And now we'd like to schedule this somewhere. So I separated this into 3 contexts. One of them is the local context, which is your laptop or your workstation, whatever that is. And then you have Jenkins, which is doing the actual building. And then Kubernetes, which runs the workload or the machine learning job. So you have a TensorFlow graph. You have the config file, as we mentioned. You push to GitLab. And the rest is basically automated. So whatever happens behind the scenes is automated. And that was the whole point behind using this setup. So we have one job, which pulls in the Docker file that we just mentioned and builds the Docker image. And this also contains, again, the dependencies. It pulls the TensorFlow graph, and it knows how to start this job. We build a Docker image that we push to a Docker registry. And then this is pulled by Kubernetes alongside a config file, a deployment file, in order to start this on Kubernetes. So remember the two resources that we had in mind. So the Docker file, the Kubernetes config. These are basically consumed by these two jobs in order to start the training. So everything beyond pushing to GitLab, in this case, is automated. So the question here comes, what's actually happening here? So again, remember the two scheduling constraints. We have machine learning machine that has to be labeled with machine learning. That's one thing. And the other thing, machine can only run one job at a time. So let's demonstrate this. So you have Jenkins, which just scheduled a job to Kubernetes. And then we have this cluster with different machines with different types. And then the question will be, what actually happens behind the scenes? How is the scheduling being done? So we try to schedule on node number 2, because this is the node which is labeled with machine learning. But then it's busy. So it's basically the same thing that we encountered before. We try the next one, and again, it's busy. So what happens is Kubernetes does the queuing for us. So it will just wait and checks for the next time until it's free, like, I don't know, every 10 seconds, every 30 seconds. I think it's actually configurable, so you can edit these parameters. And then once it's ready, it will basically schedule this job there and fetch the image. And these machines are connected to a data source, so to pull the data from, and then write back the logs. So if you have a TensorBoard URL that you'd like to access, and then you'd like to point this to some data store in order to access the logs and see your accuracies, performance, and so on, this is how you do it. So to recap this part, what we did was basically git push as a data scientist, and then the black box was doing the rest for us. So we managed to set up the environment, which was pre-built as a Docker image. We managed to rely on Kubernetes scheduling features to run and start the job. And one thing also which is interesting to keep in mind is we have everything documented. So we have the Docker files, the deployment files, everything is in Git in this case, so we can reproduce whatever the data scientist has just did. And if these models are versioned, then we can backtrack the whole process, basically, which is also interesting for us, I think, as a machine learning community. And the last part that I would like to focus on is the actual scaling. So how can we utilize or distribute work among different machines? How is this actually possible? And why do I want to do this? Because I want faster training. So the previous part was automating the process, but then the next part would be, how can I utilize more of these machines? How can I make sure that the training is actually faster? And that all of these machines are being utilized. So one case that we had in mind is, and also it was an easy win, I would say, was hyperparameter tuning. So we all know that as a data scientist, okay, you have a TensorFlow graph that you'd like to run, but in fact, you're also doing hyperparameter tuning, which means that you get a set of parameters, and then you start different runs with distinct set of parameters. So the question would be, how can I schedule these separately? How can I make Kubernetes aware of these separately to start them on different machines? So beforehand, we had everything as one job, so the whole process was being executed in one job, and tuning was sequential. So Kubernetes will start this job, I start by the first graph, I train it, I'm done, I move to the next one, and so on. So it was basically sequential. And in this case, we didn't really utilize as much as we could in this case. So the question was, what if I can distribute these runs among different machines? So we embedded, or actually it's still work in progress, so we're now embedding the hyperparameter tuning logic within the Kubernetes scheduler. So how that is done, Kubernetes has an API that everyone can use, and the scheduler has an API. So you can write your own scheduler in 10 lines of bash. And it also has a really nice Python client that you can use. So given the tuning logic that we had, and given this Python client, we managed also to write a scheduler that can know where and when to run the next tune run on a separate machine. So in this case, we broke apart the job into different tune runs, as we called them, and then each of these is running on a separate machine. And then in this case, they're running in parallel. So Beforehand, it was just one big chunk, and now I managed to separate these by letting Kubernetes know how to do the hyperparameter tuning. So that's one part. The next part could be, so if you're running distributed TensorFlow, there's a really nice tool called Kubeflow that can actually do this for you. So this, however, has to, your code needs to support that. So you need to write distributed TensorFlow code in order to be able to separate the graph among different workers. And that's kind of, it depends also on your architecture. So this didn't really apply for us as a starting point. So the tuning was actually faster in this case. But assuming that you have distributed TensorFlow and you'd like to separate the graph among different nodes, this is possible by using Kubeflow. So to recap again, what we did was separating the concerns. So machine learning from machine learning operations. Data scientists doing modeling, and the operations is being done automatically behind the scenes by using tools like Docker, Kubernetes, and Jenkins to do the scheduling, to fire these jobs. And managing environments using Kubernetes, because these environments are pre-built as Docker images, as we defined. And you can have reproducibility in the sense of you can trace back what happened by checking in Git what the data scientist has just pushed and what Jenkins has just scheduled on Kubernetes. And finally, we check the scalable solutions. So we have the hyperparameter tuning, which is possible, and also Kubeflow, which separates the TensorFlow graph among different nodes. So in this case, you have scalable solutions as well to have to utilize more hardware. That's it. Thank you.
Okay, thank you so much, Tarek. And we have time for some questions. Yes?
Thank you for the talk. I have a question. Can you elaborate a little more on hyperparameter tuning?
Yes.
Specifically, do you use something like HyperOpt or any other library that could be sort of plugged in because you could specify a whole subspace for all your...
So in this case, it was a basic grid search that we implemented. And what we did instead of, so you have a set of parameters and then you know what to start next. But by starting next, it was basically schedule the next job in Kubernetes. That's the whole difference. But the actual logic is the same that you will implement in any other setup.
Any more questions? Yes.
Hi. How do you handle credentials from the accessing databases, for instance?
We don't.
Okay.
How do you compare this with ML engine, the Google Cloud ML engine?
I think it's pretty similar in theory, like in principle. But in this case, we didn't want to resort to cloud providers for legal reasons. Okay. So we did this locally. But I think it's pretty comparable. Yeah.
Have you thought about using a queue worker in Kubernetes in order to scale the jobs?
To scale the jobs? So what do you mean?
Like there is a queue and worker in Kubernetes. So then someone can pick up the jobs and you can
yes, but in this case, you need also someone to consume these jobs in this case. So in this case, we didn't have like a consumer and a publisher. Like this setup wasn't really there. It's just a TensorFlow model that needs to be trained somewhere. So it was a matter of actually starting the job instead of having someone consuming an actual message.
Are you doing anything with respect to job priority to prevent someone from hogging the cluster?
So not yet. The question is basically about priority. So starting version 1.10 in Kubernetes, there's also, you can give priorities to pods. So this gives you the ability to do preemption, for example. So to evict pods if they have less priority. So we didn't do this yet, but it's supported.
Okay, one more question.
Hi, maybe I missed it in my toilet break, but the cluster size, is that also handled by Kubernetes? That like the amount of the capacity that you have to schedule jobs?
So the cluster size is fixed. So you have some machines which are basically there. That's how you set up the cluster. I think there are some new solutions to auto-scale this as well. So like an elastic computing cluster, basically. So to include machines on demand. Okay.
Yeah. Any more questions? Yes.
So you mentioned TensorBoard. Is it like one service somewhere outside, like a separate pod that goes like through elastic volume, or do you have a service like for every pod separately?
So how you can do it, just let me get back. So how you can do it is, if this data source is connected to your machine, you can start TensorBoard locally. So that's one thing. And one other thing that we thought about is deploying this as a service inside Kubernetes itself. And then you can expose this, and data scientists can access this with the URL. But we're doing it locally for now, because we have access to the same data source.
Okay. Any more questions? Okay. So let's give a very warm applause to Tarek.